Hi, I'm Nadeera Yakupitiyage, a master's student in agriculture and environment at the University of Sydney. In this video, I will share my research on the antibacterial potential of cinnamon bark waste distillates for fresh produce sanitation. This study is part of my capstone unit, so I hope you find it interesting. According to WHO, unsafe food causes around 600 million illnesses and 420,000 deaths annually. Among these, fresh fruits and vegetables are considered a high risk group. They are increasingly consumed for their health benefits but are highly susceptible to microbial contamination along the food supply chain, especially as there is no microbial kill step during processing. To minimize this risk, producers typically wash post-harvest using chemical sanitizers such as chlorine-based agents. However, these sanitizers have drawbacks. Their efficacy decreases under high organic loads and they can form harmful byproducts. This has led to growing interest in natural plant-based alternatives. Ceylon cinnamon or Cinnamomum verum, native to Sri Lanka, is valued for its distinct flavor, aroma, and health benefits. Sri Lanka is one of the world's leading producers and exporters of cinnamon, and its industry generates large volumes of byproducts, including thick outer bark discarded during peeling and aqueous distillates remaining after essential oil extraction, offering opportunities for waste valorization and sustainable reuse. These byproducts may contain bioactive compounds such as cinnamaldehyde and eugenol, known to inhibit microbial growth. Therefore, this study investigates whether cinnamon bark waste distillates can be repurposed as natural fresh produce sanitizers. For this study, we hypothesized that hydrodistilled aqueous distillates from cinnamon bark waste contain bioactive compounds with antibacterial properties and have potential for use as a natural household fresh produce sanitizer. Aims were to extract aqueous distillates containing bioactive compounds from cinnamon bark waste, assess their antibacterial activity against selected foodborne pathogens, identify their bioactive compounds using GCMS, and finally compare their efficacy with selected household fresh produce sanitizers. Aqueous distillates were prepared from outer bark at ITI Sri Lanka and inner bark at the University Laboratory using water-based hydrodistillation with a Cleavage apparatus as shown in the figure. Then GCMS analysis was conducted to identify the chemical composition of extracts. The oven temperature was set to 40 centigrades, then increased to 260 centigrades, and then 280 centigrades. A 30 to 1 split ratio was used, and helium injection was at 1.3 milliliters per minute. Bark distillate was injected without dilution at zero point 0.5 microliters, while cinnamon oil was diluted 1 to 500 in toluene and injected at 1 microliters. Compounds were then identified using the NIST 17.L database. Antibacterial activity was assessed using an agar diffusion assay. Outerbark distillates were tested against selected gram-positive and gram-negative bacteria at ITI Sri Lanka, while innerbark distillates were tested against E. coli alongside selected household fresh produce sanitizers at the University Laboratory. Negative control was sterile water, while positive controls were broad-spectrum antimicrobials, either gentamicin or ciprofloxacin. After incubation, inhibition zones where bacterial growth was prevented were measured. Finally, data were analyzed using one-way ANOVA followed by Tukey's test. The outerbark distillate showed no inhibition against any tested bacteria, indicating negligible activity. Therefore, data are not shown in this slide. In contrast, the inner bark aqueous distillate showed faint halos, which are unclear zones of inhibition where bacterial growth still persisted. Here, both centrifuged and uncentrifuged aqueous distillates were tested to see if removing oil droplets affected activity. But both showed similar minimal inhibition and no significant differences were observed. So these results suggest that the overall antibacterial activity of both inner and outer bark aqueous distillates is weak and negligible. Next, I compared the antibacterial activity of the inner bark aqueous distillates with selected household fresh produce sanitizers to assess their potential as natural fresh produce sanitizers. Only the citrus-based sanitizer, similar to the inner bark aqueous distillate, produced faint halos, indicating weak antibacterial activity. In contrast, the positive control ciprofloxacin and cinnamon oil showed strong antibacterial activity, highlighting the much greater potency of these treatments. Overall, the selected fresh produce sanitizers were largely ineffective, offering limited context for the comparison with the inner bark aqueous distillates. GCMS analysis of cinnamon oil identified 20 compounds with retention times ranging from 11.1 to 47.6 minutes, dominated by E-cinnamaldehyde along with minor components such as eugenol, cinnamyl acetate, benzyl benzoate, and various terpenes. The bioactive compounds identified are known for their antimicrobial properties, and this complex chemical makeup of cinnamon oil has been reported in other GCMS studies as well. Overall, the higher abundance of compounds, even when diluted 1 to 500 for GCMS, corresponds to the strong antibacterial activity observed in the well diffusion assay. Both centrifuged and uncentrifuged inner bark aqueous distillates were analyzed to determine whether removing oil droplets would alter the chemical composition. However, no significant changes were observed in their chemical profiles. Both revealed approximately 6 peaks with retention times ranging from 12.6 to 27.9 minutes. The major compound in both distillates was E-cinnamaldehyde, similar to cinnamon oil, but with lower overall abundance. Minor compounds included benzyl propenyl benzaldehyde and terpene 4-ol, while linalool was only detected in the uncentrifuged distillate. Compared to cinnamon oil, the aqueous distillates show low chemical complexity and reduced compound abundance, reflecting its weak antibacterial activity compared to cinnamon oil in the agar diffusion assay. Based on the findings, several factors appear to limit the antibacterial activity of cinnamon bark aqueous distillates. The low abundance of bioactive compounds may reduce their antibacterial effectiveness. Also, centrifugation caused no compositional change, indicating that the limited activity is inherent to the aqueous extract rather than due to oil residues. The lower chemical complexity compared to essential oil reduces overall potency, likely due to the absence of synergistic interactions among bioactive compounds in the distillates. Moreover, as most bioactive compounds present in the aqueous distillates are hydrophobic and poorly soluble in water, agar diffusion assay may underestimate their activity because these compounds diffuse poorly through the solid media. Finally, longer direct contact between the extract and bacteria could enhance antimicrobial efficacy. In conclusion, the inner bark aqueous distillates exhibited weak antibacterial activity, showing only faint inhibition compared to the strong effects of cinnamon essential oil. Then GCMS analysis revealed E-cinnamaldehyde as the dominant bioactive compound in cinnamon bark aqueous distillates along with several minor volatiles. The efficacy of the aqueous distillates could not be effectively compared with selected fresh produce sanitizers due to their weak inhibition, and since sanitizer performance depends on factors such as concentration, temperature, pH, organic matter, and contact time. Also, agar diffusion likely underestimated the activity due to the low concentration and hydrophobic nature of compounds. Nevertheless, cinnamon byproducts have the potential as natural fresh produce sanitizers if their formulation and concentration are optimized. Therefore, for future work, testing more concentrated distillates using direct contact assays like broth dilution for accurate assessment and evaluating microbial reduction and consumer safety, including toxicity, residues, and sensory effects on treated produce can be recommended. I'd like to thank the University of Sydney staff at ITI Sri Lanka and the funders who supported through the CGIAR Trust Fund. These are the references. Thank you for listening.